We saw in a previous chapter that the force method can be used to analyze indeterminate trusses, but it's ideal for trusses with a low degree of indeterminacy. The stiffness method is applicable to trusses with high degrees of indeterminacy, low degrees of indeterminacy, and even determinate trusses. But before we can use the method, we have to assemble the structure stiffness matrix, and that's the point of this problem. We'll assemble the structure stiffness matrix specifically for a coplanar or 2D truss, and the key concepts we'll use are calculating the member global stiffness matrix and combining member stiffnesses to obtain the structure stiffness. And here's our truss. It has 5 members or elements, 4 nodes, for a total of 8 degrees of freedom. The near node and far node are denoted by the arrows drawn on each member. The arrow points from near node to far node, and the degrees of freedom are labeled for each node. We're going to identify the stiffness matrix and note that AE is identical for all members. And now our approach. We'll start by calculating the member stiffness for each of the 5 members. And that's done individually. Then we'll assemble the structure stiffness from those 5 individual or member stiffness matrices. And then to check our results, we're going to ensure that it's symmetric, which helps find simple math errors. So let's get started. The member global stiffness matrix for a coplanar truss element is given by equation 14-16. A, E, and L, the length of the member, are common to each of the 16 terms in the member stiffness, and the rows and columns are organized by near node X and Y degrees of freedom, and then far node X and Y degrees of freedom. The terms lambda x and lambda y are directional cosines, which can be calculated according to equations 14.5 and 14.6. So keep equation 14-16 handy as we begin to calculate the member stiffness for each of the 5 members. Step 1. We're going to calculate member stiffness, and let's begin with member 1. Member 1 connects nodes 1 and 2, and by this arrow we see that node 1 is the near node and node 2 is the far node. The length of our member is given by this distance of 1 meter and this distance of 1 meter. If we take the square of the x length, add the square of the y length, take the square root, we get an overall length of the member of 1.414 meters. Now our directional cosines. Lambda x, we saw, is the change in x coordinate over the length. But my change in x coordinate from near node to far node is negative in this case, so I have a negative 1 meter over the length. So my directional cosine in the x direction is a negative 0.707. In the y direction, near node to far node y coordinate is negative, and again the length is 1.414 meters, and so this directional cosine is also a negative 0.707. Now if we look at equation 14-16, there are some terms repeated often. Directional cosine in the x, lambda x squared, lambda x times lambda y, and lambda y squared. And sometimes there's a negative sign in front of those. But all of these terms involve one of those three. And we'll pull the length inside. So let's calculate those three. Lambda x squared divided by L will be a negative 0.707 squared divided by 1.414 meters, and that equals a 0.5 divided by 1.414 meters, and that quantity is a positive 0.3536 per meter. Lambda y squared over L. We have a negative 0.707 squared divided by 1.414, which we just calculated, that's 0.3536 per meter. The interesting units are because each of these terms would be multiplied by AE. And AE together give a unit of force. So our coefficients, our stiffness coefficients, are force per distance. Lambda x times lambda y divided by L is a negative 0.707 for lambda x, a negative 0.707 for lambda y, divided by the 1.414 meters, and this one is also 0.3536 per meter. So let's assemble this into the element stiffness matrix in global coordinates. I'll call that little k, and its subscript 1 refers to element 1. AE is common to all of the terms. Our matrix has 4 rows and 4 columns, and I'm going to label the degrees of freedom. Number 1, 2, near node, x degree of freedom is 1, and then degree of freedom 2. Far node, x degree of freedom is 3. Y degree of freedom 4. So my rows carry the same sequence of degree of freedom numbers. Now from our equation 14-16, our first term is lambda x squared, then we'll have lambda x lambda y, then minus lambda x squared, and minus lambda x lambda y, which for this element is 0.3536 per meter, a 0.3536 per meter. The next one is minus the lambda x squared and minus the lambda x times lambda y. Our second row, lambda x times lambda y squared minus lambda x lambda y minus lambda y squared. which gives us 0.3536 per meter, 0.3536 per meter, a minus 0.3536 per meter, and minus lambda y squared, so a minus 0.3536 per meter. Our third row, minus lambda x squared, minus lambda x lambda y, lambda x squared, lambda x lambda y. Minus lambda x squared is a minus 0.3536 per meter. The minus lambda x lambda y, minus 0.3536 per meter. Positive lambda x squared, and the positive lambda x lambda y. Our last row for this element, minus lambda x lambda y, minus lambda y squared, positive lambda x lambda y, and positive lambda y squared. So we have a minus the lambda x lambda y, minus the lambda y squared, and of course all of these were divided by L, the positive lambda x lambda y, and the positive lambda y squared. Now let's make a quick check. This matrix should always be symmetric. Well, all of the magnitudes are identical for this particular element, so that aspect of the symmetry is met. And so as we look down the diagonal, this side should mirror this side, and we'll check positive and negative signs. These two share the same sign. These two share the same sign. These two share the same sign. This one and this one share the same sign. These two share the same sign, and these two share the same sign. The other thing we check for is, notice the diagonal itself always has lambda terms squared. So even if lambda is negative, when we square it, the diagonal should always be non-negative, a positive quantity or a zero for the element. And in this case, we have all positive entries on the diagonal for the element. Now member 2. We'll start by finding the length of our member. Member 2 connects nodes 2 and 3. This arrow indicates that node 2 is the near node, node 3 is the far node. Our degrees of freedom are numbered. Notice that x is 3, y is 4. Here x is 6, y is 5. And we'll explain more of why we chose that numbering system later. To get the length, we'll see that the height of the piece is 1 meter, and the width of the piece is 1 meter. So we take square root of the 1 meter squared plus 1 meter squared, and this element is also 1.414 meters long. Lambda x for this element. The x coordinate changes in a negative way, and so lambda x is a minus 0.707, just as for member 1, and lambda y is also minus 0.707, just as it was before. So let's solve for our three quantities that will show up on a recurring basis. lambda x squared over L, just as we calculated for member 1, will be 0.3536 per meter. Lambda y squared over L will be 0.3536 per meter, just like we calculated for member 1. Lambda x, lambda y over L will also be 0.3536 per meter. So we should expect that the element stiffness matrix in global coordinates will be identical to the one we calculated for member 1. It has the same length, the same A and E, and the same directional cosines. The degrees of freedom, however, are now 3, 4, 6, and 5. Near node x, near node y, far node x, far node y. The rows, therefore, 3, 4, 6, and 5. And if we assemble the stiffness matrix according to equation 1416, we get lambda x squared over L 0.3536 per meter, lambda x lambda y over L 0.3536 per meter, minus lambda x squared, so a minus 0.3536 per meter, and a minus lambda x lambda y minus 0.3536 per meter. Lambda x lambda y, lambda y squared minus lambda x lambda y, and minus lambda y squared. Then a minus lambda x squared, a minus lambda x lambda y, lambda x squared, and lambda x lambda y. Minus lambda x lambda y minus lambda y squared, positive lambda x lambda y, and a positive lambda y squared. All of those, of course, divided by length, which gives us the units we have. Again, we check symmetry across the diagonal. All the magnitudes are the same, and so all I needed to do is check for minus signs, and the positive and negative signs are mirrored on the diagonal, or off the diagonal, and the diagonal is non-negative. So this member stiffness appears to be ready. Now member 3. Member 3 connects node 3 to node 4. Node 3 is its near node based on this arrow. Node 4 is its far node. And the degrees of freedom are in sequence 6, 5, 7, 8. And it is 2 meters long. It has a directional cosine for the x direction, 0 divided by 2 meters. So that is 0. The change in y coordinate is a positive 2 meters. Its length is 2 meters. So the directional cosine in the y direction is a positive 1. We put those together. Lambda x squared divided by L will therefore be 0 because lambda x is 0. Lambda y squared divided by L will be 1.0 squared divided by 2 meters, which equals 0.5 per meter, and lambda x, lambda y over L equals 0 because lambda x is 0. So our element stiffness for element K3, or element 3, AE times, and our columns are associated with degrees of freedom: 6, near node in the x, near node in the y, 5, far node in the x, 7, far node in the y, 8. Rows are associated with the same degrees of freedom in the same sequence. Our first entry, lambda x squared over L, 0. Lambda x lambda y, 0. Minus lambda x squared, 0. Minus lambda x lambda y, 0. Lambda x lambda y, 0. Lambda y squared over L, of course, 0.5 per meter, minus lambda x lambda y, and minus lambda y squared over length, minus lambda x squared, minus lambda x lambda y, lambda x squared, lambda x lambda y, minus lambda x lambda y, minus lambda y squared, lambda x lambda y, and a positive lambda y squared. Again, we're symmetric with respect to the diagonal, and the diagonal is either 0 or positive. Number 4. The near node is node 3, the far node, node 4. So my degrees of freedom are 3, 4, 7, 8. The change in x coordinate is 1 meter, and the change in y coordinate is 1 meter, so my length is the square root of 1 meter squared plus 1 meter squared is 1.414 meters long. Directional cosine in the x direction. Its change in x coordinate is negative over the 1.414 meters, so we have a negative 0.707. Directional cosine in the y coordinate changes in the positive direction, so it is a positive 0.707. So lambda squared, lambda x squared divided by L will be a negative 0.707 squared divided by the 1.414 meters, which equals a positive 0.3536 per meter. Lambda y squared per L, divided by L rather, a positive 0.707 squared divided by 1.414 meters, is a positive 0.3536 per meter. And lambda x, lambda y divided by L in this case will be a negative 0.707 times a positive 0.707 divided by 1.414 meters, and this will be a negative 0.3536 per meter. So our stiffness for element 4 is AE times 4 rows and 4 columns of numbers of stiffnesses, and my first degree of freedom is near node X, then near node Y, far node X, then far node Y, and our rows are labeled the same way: near node X, near node Y, far node X, far node Y. So lambda x squared divided by L, 0.3536 per meter. Lambda x, lambda y divided by L, a negative 0.3536 per meter. Negative lambda x squared, and a negative lambda x lambda y over L gives me a positive coefficient, 0.3536 per meter. The lambda x lambda y, negative 0.3536 per meter. Lambda y squared, negative lambda x lambda y, and so the negative signs cancel, and a negative lambda y squared. Negative lambda x squared, negative lambda x lambda y, so the negative signs cancel, lambda x squared, and lambda x lambda y, which is negative. Negative lambda x lambda y, so the negative signs cancel. Negative lambda y squared, lambda x lambda y, and lambda y squared. So we check symmetry about the diagonal, and all magnitudes are the same. The positive signs and negative signs are symmetric about the diagonal, and the diagonal is all non-negative. And our last member, member 5. Which has near node, node 1, and far node, node 4, based on the direction arrow, and degrees of freedom 1, 2, 7, 8. The length of the member is 2 meters. Lambda x is a negative 2 meters, since the x-coordinate is negative, or changes in a negative direction, divided by the 2 meter length, and so we have a negative 1.0 for lambda x. The y-coordinate does not change, and so lambda y is 0. So lambda x squared divided by the length is a negative 1 squared divided by 2 meters is a positive 0.5 per meter. lambda y squared over the length is 0. Since lambda y is 0, lambda x lambda y over the length is 0, since lambda y is 0. And so our stiffness for element 5 is AE times, and our degree of freedom sequence is near node X, near node Y, far node X, far node Y. Same sequence for the rows. Lambda x squared, a positive 0.5 per meter. Lambda x lambda y minus lambda x squared. Of course, all of these are divided by L. Minus lambda x lambda y. Lambda x lambda y. Lambda y squared minus lambda x lambda y minus lambda y squared minus lambda x squared minus lambda x lambda y, lambda x squared, lambda x lambda y minus lambda x lambda y minus y squared, lambda x lambda y, and lambda y squared. It is symmetric about the diagonal, and the diagonal is all non-negative. And now step 2. Let's assemble the structure stiffness matrix. And the structure stiffness matrix will denote by capital K, and it equals summation of the member stiffness for each of the members of the structure. But that summation is done by degree of freedom. So for example, the entry or coefficient 1, 1 in the structure stiffness refers to the force generated at degree of freedom 1 due to a unit displacement at degree of freedom 1. And that is given by K11 from member 1 plus K11 from member 2 plus K11 from member 3 plus K11 from member 4 plus K11 from member 5. And again, the subscripts 1, 1 refer to the force generated at degree of freedom 1 due to a unit deformation at degree of freedom 2. So if we look back at member 1, degree of freedom 1, 1, or coefficient 1, 1, is AE times 0.3536 per meter. Then we add the contribution from member 2, but degree of freedom 1 is not represented in member 2, so its contribution is 0. From member 3, again we have no representation of degree of freedom 1. Member 4, no contribution from degree of freedom 1, or to degree of freedom 1 I should say. Member 5, we have coefficient 1, 1 is AE times 0.5 per meter. When I put those all together, my structure stiffness coefficient for degree of freedom 1, degree of freedom 1, that is unit force generated in degree of freedom 1 due to unit deformation in degree of freedom 1, is the AE times 0.8536 per meter. Now let's look at coefficient 1, 2. That is force at degree of freedom 1 due to unit deformation at degree of freedom 2. Same idea. Now if we look at something we observed in calculating the coefficient 1, 1, if the member does not connect or touch the degree of freedom, then it has no contribution to the stiffness. So member 1 touched degree of freedom 1, it contributed. Member 2 did not touch degree of freedom 1, it did not contribute, nor did member 3 or 4, but member 5 did. So when we look at degrees of freedom 1 and 2, that is the force generated at degree of freedom 1 due to unit deformation at degree of freedom 2, again, we expect member 2, 3, and 4 not to contribute. So let's check that. First, member 1. Coefficient 1, 2 refers to the degree of freedom of the force, that is the rho, and then the degree of freedom of the deformation, that is the column. So our coefficient is 0.3536 times AE. Then we'll check that member 2 does not contribute to this coefficient, and it does not, nor does member 3, nor does member 4. Member 5 does have those degrees of freedom, and so row 1, column 2, we want this entry, which happens to be 0. So the remaining contributions to our coefficient are all zeros, and so our coefficient for the structure stiffness, AE, times 0.3536 per meter. We need to continue this process for all the combinations of coefficients. Let me jump to all the combinations of degrees of freedom, that is, to give us the coefficients. So let me jump to 1, 5, which is the force generated at degree of freedom 1 due to deformation in degree of freedom 5. And so again, it's the contribution from each of the members added up. And if we look at member 1, we have degree of freedom 1, but not 5. So its contribution is 0. For member 2, we have degree of freedom 5, but not 1. So its contribution is 0. Member 3, we also have degree of freedom 5, but not 1. For member 4, it doesn't connect to either of the degrees of freedom. And member 5. We have degree of freedom 1 but not 5. So in this case, the coefficient is 0. And what we can learn from that is if there is no single member that connects 2 degrees of freedom, then the structure stiffness, the capital K coefficient, will be 0. Well, that'll save us a little bit of time. Now let's jump to coefficient 3, 3. That is the force generated at degree of freedom 3 due to unit deformation in the direction of degree of freedom 3. We add the contribution from the first element or member, the second member, third member, fourth member, and fifth member. But we've learned something now. As we look at degree of freedom 3, member 3 does not connect to this node, so its contribution will be 0. And member 5 does not connect to this node, so its contribution will be 0. But members 1, 2, and 4 all meet at that node, so we need to look up what their contribution is. So starting with member 1, row 3, column 3, AE times 0.3536 per meter, to which we add from member 2, degree of freedom 3 in the row and degree of freedom 3 in the column, AE times 0.3536 per meter. And we add from member 4, row degree of freedom 3 and column degree of freedom 3, this quantity, when we add those together, we get 1.0608 per meter times AE. Well, let's try one more, and then we'll show the assembly of the structure stiffness. Now let's try coefficient 5, 6. That is force generated at degree of freedom 5 due to unit deformation at degree of freedom 6. Now I want to point out, even though degree of freedom 6 is restrained to move, we calculate our coefficient as if it could move. The fact that it's restrained shows up later in the process, after we have already assembled the structure stiffness. So we'll use that fact in the next example. Using what we've learned so far, for coefficient 5, 6, we'll get a contribution from member 2 and member 3, but not members 1, 4, and 5. So we will abbreviate our algebra here to reflect that knowledge. So let's look at member 2. We need row degree of freedom 5 and column degree of freedom 6. Now remember, we picked our degree of freedom numbers so that they are out of sequence, and we'll see why in the next example, but what we need is this contribution. to which we add from member 3 row degree of freedom 5, column degree of freedom 6, a coefficient that is 0. So our structure stiffness coefficient is AE times 0.3536 per meter. So now let's assemble our structure stiffness matrix. There are 8 degrees of freedom to the structure, so our capital K matrix will have 8 columns and 8 rows, each in increasing order of degree of freedom number. All the terms have AE in common, so I've pulled that outside the front. And let's work in chunks, 2 by 2 chunks, because there are 2 degrees of freedom at each node. So if we look at 1, 1, we calculated that one and found it to be 0.8536 per meter. For coefficient 1, 2, we calculated it to be 0.3536 per meter. Then if we look at 2, 1, only members 1 and 5 contribute, and when we add up its components, or the contributions from each of those members, we get 0.3536 per meter. Degree of freedom, or coefficient 2, 2, also is common only to members 1 and 5. And so when we add up the contributions from those 2 members, we get a 0.3536 per meter. Now, this chunk, the forces generated in degrees of freedom 1 and 2 due to deformations at degrees of freedom 3 and 4. The only things that will contribute to this chunk are members that connect degrees of freedom 1 and 2 to 3 and 4. And the only member that does that is member 1. So if I go back to the member stiffness for member 1, rows 1 and 2, columns for degrees of freedom 3 and 4, means this whole chunk becomes the entries in our structure stiffness matrix. So I'll write those in. Now our next chunk. Forces at degree of freedom 1 and 2 due to deformations at degrees of freedom 5 and 6. And those degrees of freedom are here, and no element connects those directly. So these coefficients are all 0. Now for this chunk. There's only one member that connects degrees of freedom 1 and 2 to 7 and 8, and that's member 5. So the structure stiffness matrix in that chunk is directly taken from this member stiffness. Now the next chunk. Forces at degrees of freedom 3 and 4 due to deformations at degrees of freedom 1 and 2. Again, only member 1 connects these degrees of freedom. So our structure stiffness pulls directly from the member stiffness here. Now our next chunk, 3, 4, and 3, 4, which means forces generated at degrees of freedom 3, 4, and 4 due to deformations at degrees of freedom 3 and 4, which will have a contribution from member 1, 2, and 4. And when we take all of those contributions and add them up, one of them we saw is 1.0608 per meter, and we would calculate the remaining coefficients to be 3536 per meter, per meter, and 1.0608 per meter. Now our next chunk. Only one member connects degrees of freedom 3, 4, and 5, 6, and that's member 2. So we're talking about degrees of freedom at the rows 3 and 4, degrees of freedom at the columns of 5 and 6. But notice, this one is 5, this one is 6. In the structure stiffness matrix, these two come to the left of these two. Now in this case, they're identical, but you need to be careful to not get that confused. Because of our numbering system, these two have to reverse or change positions. And so we insert those. In our next chunk, only one member connects degrees of freedom 3, 4, and 7, 8, and that's member 4. So we take rows associated with degrees of freedom 3, 4, columns associated with degrees of freedom 7, 8, and we take this chunk out directly and put it into the structure stiffness. Now our next chunk. Force generated at degrees of freedom 5 and 6 due to deformation at degrees of freedom 1 and 2. And since there is no member that connects directly between these degrees of freedom, these coefficients are 0. Our next chunk comes only from member 2. We have rows associated with degrees of freedom 5 and 6, columns associated with degrees of freedom 3 and 4. Note that because of our numbering convention, as we put this chunk into the structure stiffness matrix, this one goes above this one. But it turns out in this case they're identical. That won't be true always, so we need to be careful. Now our next chunk. Members 2 and 3 meet at this node where degrees of freedom 5 and 6 are. So we add the contribution from each of those two members, careful that we denote or that we recognize degree of freedom 5 and 6 will be put in that sequence into the structure stiffness matrix, but in the element matrices they are in reverse order. And when we add those up, we get 0.8536 per meter, 0.3536 per meter, which we had calculated on the previous slide, 0.3536 per meter, and 0.3536 per meter. Now this chunk, which only comes from member 3, we're looking for force generated in degrees of freedom 5 and 6 due to deformations at degrees of freedom 7 and 8. Note that these two go above these two, and so we have the following coefficients. Now this chunk, forces at degrees of freedom 7 and 8 due to deformations at degrees of freedom 1 and 2. These come only from member 5. So we pull this chunk directly from the member and insert it for the structure. Now our next chunk. Degrees of freedom 3 and 4, 7 and 8 are connected only by member 4. We're looking for rows associated with degrees of freedom 7 and 8, columns associated with degrees of freedom 3 and 4. So this chunk carries over directly to the structure stiffness matrix. Now this chunk, which comes only from member 3, rows associated with degrees of freedom 7 and 8, columns associated with degrees of freedom 5 and 6, so we need to take these and then these and insert them directly into the structure stiffness. Now our final chunk, which has contributions from members 3, 4, and 5. When we add up the contributions at degrees of freedom 7 and 8 for both the rows and columns, we get the following structure stiffness coefficients. Now step 3. Let's check symmetry. Usually, the structure stiffness matrix is not the end of the problem, but is actually an important ingredient in the analysis process. So we're looking for a good intermediate check to make sure we've not made a silly math error in the construction of our structure stiffness matrix. Then once we use it in later example problems, we'll be able to check our results for reasonableness. And so how we'll check intermediately is to make sure that our matrix is symmetric about the diagonal. And here's our diagonal. We also want to make sure that our diagonal is non-negative and all of these quantities are positive. And so we begin checking magnitudes and signs across the diagonal. These two are identical. These two are identical. These two and these two. These zeros and these two. These two zeros. These two zeros and these two. These zeros, these two quantities. We look over here in the corners, this zero and that, this quantity and this, and these two. Then here and here, this one and this one, this one and this one. Then here and here, this one with this one, and then these two. Then the negative quantity here and here, and the two zeros. The negative quantity here and here, and then these pair. This zero with this zero, and these two. So it passes our check, and we can use this matrix in future example problems. Now let's go back and review our process. We started by finding the member stiffness for each of the 5 members individually, and to do that we used equation 14-16 and noting that the directional cosines are given by equations 14-5 and 14-6. We started with member 1, noting which direction the member goes, so we could identify near node and far node. Then member 2, again first identifying near node and far node. Then member 3, member 4, and member 5. Along the way, we always checked to make sure that the matrix was symmetric and that the diagonal terms were all either 0 or positive. We then assembled the structure stiffness by adding up the coefficients from each of the 5 members, and we observed that if a member does not meet at those degrees of freedom, then it does not contribute to the structure stiffness. For example, members 2, 3, and 4 do not meet where degrees of freedom 1 and 2 are, so none of those members contributed to stiffness coefficient 1, 1, or 1, 2, or 2, 1, or 2, 2. We also observed that if no member connects to degrees of freedom, and those degrees of freedom are not at the same node, for example, degrees of freedom 1 and 5, then the structure stiffness is 0. We also observed that because of our numbering convention for degrees of freedom, which we chose to help us in future examples when we use the stiffness method, that we have to be careful when assembling the structure stiffness matrix because these are out of sequence when we pull chunks out of the member stiffness to put into the structure stiffness. We assembled all of those coefficients, an 8 by 8 matrix for this structure, and then we wrapped up by checking symmetry, which will often identify if we've made a math error. I'll also point out that each of these 64 coefficients are multiplied by AE, which was constant for all members of the truss. Well done!